Alright, so today we are looking at what's called reciprocal circular functions. Alright, so the word reciprocal, whenever we're looking at the word reciprocal, it means 1 over, and circular, sine cos tan. So the reciprocal circular functions are 1 over those particular things, and they are defined as the following. Full name, cosecant. Normally we would see it written as cosec. I know mathematicians like to shorten things if possible. So cosec theta, and it is 1 over sine theta. The one that's related to that is secant, and again we just usually write that as sec theta, and that is 1 over cos. And the final one is cotangent, or cot, and that's 1 over tan. And since we know that tan is sine over cos, if we turn it upside down and multiply, we can also write that as cos theta on sine theta. All right, so the handout that I've given you, and stick that in your bound reference. All right, so it gives you the graphs of, so the first one I've got is cosec on the front. So here's our sine graph, and so is cosec is 1 on sine, and the bottom is the graph of that, and as you can see, so you've got some asymptotes, because so whenever sine is 0, we would have 1 over 0, which would be undefined, of course. So we've got asymptotes at each of those places. All right, the bits above the axis go down to 1, and the bits below the axis come up to -1. Again, there's a period, so negative pi to pi, for example, or 0 to 2 pi, so still 2 pi period. All right, so there's your cosec. Your sec one's related to cos, which we've got there, so the same sort of pattern where cos is equal to 0 is where you would have your asymptotes, and again comes down to 1 up to -1. And there's more information there. And then your cot one, so here's your tan graph up here, and then your cot's down the bottom there. So again, the same kind of thing, where tan is 0, so it's 0, pi, 2 pi, that's where you have asymptotes. And the location where the asymptotes were actually crosses through the axis there for cot. All right, so we can use certain things on that to help us draw some graphs. So let's have a look at a couple of graphs. So, example. So sketching between 0 and 2 pi, y equals cosec 2x, and the other one, y equals sec x plus y on 3. Okay, so the patterns of these values, like the 2 in here, the plus pi on 3, they have the same effect on these graphs as any others. So this 2 in front of the 2x here is what? What does that represent? A dilation, yep. And this pi on 3 here is a translation. All right, so all the same kind of things apply. And our period, so period for cosec is related to the period of sine, which is 2 pi on n, and n in this case is 2. So it's 2 pi on 2, which is pi. All right. So for cosec, we know cosec has asymptotes. And the first asymptote, given that there's no translation in this case, our first asymptote would be at 0. So remember cosec, just a little rough sketch here, cosec relates to sine. Remember sine goes like so. And so our asymptotes for cosec relate to these zeros. And if we've got a period of pi, that's 0, that's pi on 2, that's pi there, and so on. So our asymptotes relate to those points there. So 0, pi on 2, and pi. Don't need to go any further than that, because, oh no, we do need to go further than that. So the next one would then be 3 pi on 2 and 2 pi, I believe. Because we're asked to do between 0 and 2 pi. So, right, so let me draw in my asymptotes. There's my asymptotes. All right.
Do you have to draw in the asymptote lines, or?
That would be very good practice to always draw your asymptotes in, yes. I would. If there's a graph that's got asymptotes, yes, I would always put them in. All right, so next. So the highest point here is 1. The lowest point here is -1. Of course, cosec is 1 over sine. So here it's 1 over 1, which of course is 1. There it's 1 over -1, which of course is -1. And that occurs, of course, because of the cyclic symmetry kind of properties. It occurs halfway between. So halfway between these two asymptotes, we have the point that corresponds to that, which is there. And then it goes like so. And halfway between the next one, which is the point that corresponds with that, and then curves around like so. And then to finish it off, what do I need to do? Just repeat what I've already got, yeah? And so there is our graph. All right. All right, anything about that you're not clear on, that you want me to clarify before we move to example B? No. All right, so example B. Part B, example B, what do you want to call it, was, rubbed it off, sec. All right, so our period, again, it's 2 pi on n, related to the period of cos, and so in this case it's 2 pi. The pi on 3s we've already talked about is a translation. The question is, which way is it translated? Left? Yep. Okay, now, in a couple of things. So normally, for cos, like cos over here, so normally here's our cos, there's cos is 0 at pi on 2, alright, so what that then relates to is the sec of pi on 2 is undefined, yeah?
I was not supposed to be cos, yeah.
Yes? And so what that means, this means asymptote, yeah? But because we've got a translation, our first asymptote then is not at pi on 2, but pi on 2, and because it's moved to the left, minus pi on 3. You with me? Good. Common denominator of pi on 6, so it's 3 pi on 6 minus 2 pi on 6, so which is pi on 6. Alright, let's have a look. Zero to 2 pi. So if I break these into, it's not very good. So I'm putting put some extra lines in here. And these extra lines in here. Pi on 6, so each one of these is pi on 6. Yep. So our first asymptote is at pi on 6. So that's here. Then 1 period later, so 2 pi later, there would be another asymptote, which would be out here somewhere. We don't want that bit. But halfway, there's going to be the asymptote that relates to that point there, which is between asymptotes, half a period, isn't it? Alright, so which is pi. How many sixths in pi? 6. So we'll go 1, 2, 3, 4, 5, 6. So that's here. Alright, I'm going to draw this underneath bit. That's the bit that corresponds to this. So halfway between those two, which is here, it's down there. Goes like so. Then this one over here, which would be this bit over here, that's 1, 2, 3, 6, 1, 2, 3, 6. Go like this. Now, the thing is, in our domain we're asked to do between 0 and 2 pi. So what I really need to do is I need to know what's going on here. Where is it here? And so I just do a substitution. So when x equals 0, y is equal to the sec of 0 plus pi on 3, which is equal to the sec of pi on 3. Whoops. And sec is 1 on cos. And what's the cos of pi on 3? Root 3 on 2, 1 over 2 on root 3, or 2 root 3 on 3, and so then you need to make an estimate of where that might be, and then of course at the end here that's where that I've done very well there with that. Let me move it so it looks better. So these 2 points should be on the same level because they're 1 period apart, yeah? Alright, so that's that there. Alright, a little bit of messy, a little bit of mucking around there, but if you take your time and go step by step, you'll get there. Alright, anything about that anyone wants to, before we move on? Alright, so we can also solve equations with those inverse or reciprocal circular functions. So we'll do some examples of the equations. Sorry, got ahead of myself. Find the exact value. So I'm using to find exact values. So the first one is sec 11 pi on 4. The second one is cot 11 pi on 3. Alright, so the way I would do is go rough sketch, 11 pi on 4. Question is where is that? So 1, 2 pi on 4, 3, 4 pi on 4, 5, 8 pi on 4, and then we've got to go another 1, 2, 3 out to there. Would that be correct? So the key angle that we're interested in, call it the reference angle, that's what I always call it. The reference angle is this one in here. And if that's 11 pi on 4, that angle around there, what's this blue one I've just done? Pi on 4. Correct. All right, so what's sec related to? Sec's related to 1 over cos. Yep. So sec 11 pi on 4 is related to 1 over cos of 11 pi on 4. 1 over, so let's think about cos. So, cos here, second quadrant, so cos is negative root 2 on 2, turn it upside down, multiply, negative root 2 on 2, whoops. Rationalise, so expectation is we always have rational answers. So you've got 2 root 2 or negative 2 root 2 on 2, 2's cancelled, negative root 2. Yes? Alright, a little bit of fiddling around. So we can look at the cot in a similar way. So 11 pi on 3, 11 thirds pi, so there's 6 thirds, 3 thirds there, 6 thirds, 9 thirds, 10, 11 thirds. Finish up here, would that be correct? Start here, 3 thirds, 6 thirds, 9 thirds, 10, 11 thirds. Got it right? So my reference angle that I'm interested in is this one, which is pi on 3. Yep. So my cot of 11 pi on 3 relates to 1 over 10 of 11 pi on 3. And we're in the which quadrant? fourth, so tan is negative in the fourth quadrant.
Yeah.
And it relates to pi on 3. So grab my triangle. 2, 1 root 3, pi on 3. Tan is opposite over.
Is root 3.
So yeah, root 3 over 1, which is just of course 1 over negative root 3. Need to rationalise expectations, rational denominators. So negative root 3 on 3. All right, anything about that second one? No. If I'm going through the arithmetic too fast and you lose where I'm up to, just make sure you give me a yell. All right, we can also have equations that we can simplify. Or expressions we can simplify. Alright. So, let's simplify that. Any suggestions? What suggestions have we got? Can we do anything with the numerator, the top line there? Yes? No? Cos x minus cos cubed x. Is cos a common factor or not?
Yeah.
Yes! Alright, so let's take cos out as a common factor. And when we do that, we've got 1 minus cos squared. Yes?
Yeah.
Cot, can we do anything with that?
Turn it into sine times sine over. No, cos over sine, sorry.
Turn it into cos over sine, that's a good idea. And now we're, oops, better use x, be consistent with the question. And if we're dividing by a fraction, we would flip it and multiply. And then, what happens? Doesn't that and that cancel? Yes? Now, there's something else that can be changed here as well. One minus cos squared x. Can do something with the 1 minus cos squared x.
That's equal to sine squared.
It is, because remember sine squared plus cos squared is equal to 1. So sine squared is 1 minus cos squared. So that there is sine squared x times by sine x. So our final answer is
Sine cubed.
sine cubed x. Yep. All right, one last example. And that's what I was.
Is this related to the
Well, it's the reciprocal circular functions,
Yeah,
isn't it?
right.
Because the cot's one of the reciprocal. So yeah, it's related. So it's stuff you've done before, but now
Yeah.
we're bringing the same here.
Yeah.
This is stuff you've done before, but now we're bringing the reciprocal functions into it.
Okay.
And the same with this next example, what I'm going to do is the stuff you've done before, but it's now got reciprocal functions in it. Now, but this next example I'm just going to do so up here sine squared plus cos squared is equal to 1. Now I can go two ways with that. So if I divide everything by sine, for example, then I'll have sine squared, I should say. I'll have sine squared x over sine squared x plus cos squared x over sine squared x equaling 1 over sine squared x. This bit here is equal to 1. Cos on sine is cot. And 1 on sine is cosec.
Wait, you look. So what have you done from the first equation?
So sine squared plus cos squared equals 1.
Yeah.
I've divided everything by sine squared. Alright, so in terms of our reciprocal functions, this one here is related to our cos squared sine squared. Now I could also divide everything by cos squared. And if I divide everything by cos squared, I'll have sine squared over cos squared plus cos squared over cos squared equals 1 over cos squared. Alright, and so sine on cos is tan, so that's tan squared plus 1 is 1 on cos is sec. And so again, there's another version. So these three things, they're all related to each other. And now we're going to use them. So like I said, this example here, you've done stuff like this before. So if tan x, excuse me, is equal to 2, and x is between 0 and pi on 2, we want to find these things. Sec x and cos x, cos x. All right. So, A, we want sec x. That's what we're after. So if I come over here, and what I've just done, and I'll look here, with these two, this one here, we've got sec squared there. All right, we've got tan squared in there as well, and we've been given tan, so we can use those things. All right, so what we know is that sec squared x is equal to 1 plus tan squared x. And we know that tan is 2, so 2 squared, so sec squared would be 5, wouldn't it? Now we're asked for sec, not sec squared. And so that then would hopefully be plus or minus root 5. Is that the answer? It's another bit of information here. Right. It says that x is between 0 and pi on 2. So between 0 and pi on 2, which quadrant's that? First quadrant. And in the first quadrant, what do we know about our circular functions, sine, cos and tan?
All positive.
All positive, so is sec going to be positive in that quadrant as well?
Yeah.
Yep. First quad, so sec x is the positive root 5 bit. All right, the next one is cos. So what's cos related to? Sec. And cos is, well, if sec is 1 on cos, cos would be 1 on sec, yeah. Yep. So B. So cos x is 1 over sec x. And we've just found that up in the part A, have we not? So 1 on root 5. Don't forget to rationalise your denominators. So you get root 5 on 5 for that answer. All right, anything about that? No. Okay. So yeah, a lot of those, some of those things we've done before, just with sine, cos and tan, but now we're adding those reciprocal sec, cosec and cot into the mix. Processes are the same, we just got to keep in mind how sec, cosec and cot are related to sine, cos and tan.
You made a mistake.
Where have I made my mistake?
No, in a previous example.
Oh, why didn't you tell me when I made it?
Because I didn't actually think of it then. You said that cos of pi on 3 was root 3 on 2, it's actually a half.
Oh yeah, it is too. I did sine.
Yeah.
Oh no. Like, people in YouTube land,